Good day, everyone. Today, our topic is all about interspecific competition. The concept of interspecific competition is a cornerstone of evolutionary ecology. Darwin based his idea of natural selection on competition because it has been regarded as the major force behind species divergence and specialization. First off, let us define interspecific competition. Interspecific competition is a form of competition between individuals of different species for shared resources, such as space and food in the same ecological area. It is different from intraspecific competition because intraspecific competition occurs between members of the same species, but interspecific competition occurs between members of different species. For example, squirrels compete among themselves for acorns during a year when oak trees produce fewer acorns. This is intraspecific competition. However, at the same time, wild turkey, blue jay, and mice vie for the same resource, which is the acorns. And this is interspecific competition, which is competition between individuals of different species. Interspecific competition takes two forms: exploitation and interference. Exploitation is when organisms use up resources directly, which will no longer be available for other species to use, while interference is when one organism prevents other organisms from using the resources. Thomas Schoner of the University of California, Davis proposed that six types of interactions are sufficient to account for most instances of interspecific competition. First is consumption. This is when individuals of one species inhibit individuals of another by consuming a shared resource, such as the competition among various animal species for acorns. Next is preemption, which occurs among sessile organisms such as barnacles, in which the occupation by one individual precludes the establishment by others. Third is overgrowth, which occurs when an organism literally grows over another, inhibiting access to some essential resource. An example of this is when a taller plant shades those individuals below, reducing available light. Fourth type is chemical interaction. It is when chemical growth inhibitors or toxins released by an individual inhibit or kill other species. One example is allelopathy in plants, in which chemicals produced by some plants inhibit germination and establishment of other species. Fifth is territorial. This results from the behavioral exclusion of others from a specific space that is defended as a territory. Lastly is encounter. This results when non-territorial meetings between individuals negatively affect one or both participant species. In the early 20th century, two mathematicians, the American Alfred Lotka and the Italian Vittorio Volterra, independently arrived at mathematical expression to describe the relationship between two species using the same resource. This is known as the Lotka-Volterra Model. The Lotka-Volterra model describes the relationship between two species using the same resources. It can also be used to understand how different factors affect the outcomes of competitive interactions. Both men began with a logistic equation for population growth. The logistic equation here models a rate of population increase that is limited by intraspecific competition. Now, let's dissect this equation. So dn1 over dt refers to the population growth. Specifically, it refers to the population growth of species 1, while dn2 over dt refers to the population growth of species 2. Next is R2. It is the intrinsic rates of increase of species 2, while R1 is the intrinsic rates of increase of species 1. N1 is the population size of species 1, while N2 is the population size of species 2. Last variable, K2 is the carrying capacity of species 2, while K1 is the carrying capacity of species 1. The carrying capacity represents the maximum sustainable population size that can be supported by the available resources. The first term on the right side of the equation, which is Rn, describes the population's growth in the absence of competition, while the second term, which is 1 minus n1 over k1, incorporates intraspecific competition or density dependence into the model, which takes a value between 0 and 1. The addition of this term describes a rate of population growth that slows down as population size increases, until the population reaches its carrying capacity. The logistic growth equation on the previous slide can be modified to include the effects of interspecific competition as well as intraspecific competition. The big difference between the previous equation is the addition of alpha and beta, which are the competition coefficients. The competition coefficient represents the effect that one species has on the other. So for species 1, alpha refers to the per capita effect of species 2 on species 1, while beta refers to the per capita effect of species 1 on species 2. The carrying capacity for species 1 is K1, and as N1 approaches K1, the population growth dN1 over dt approaches 0 as well. However, since this is interspecific competition, species 2 is also vying for the limited resource that determines K1. Thus, the total effect of species 2 on species 1 is alpha N2. And as the combined population, N1 plus alpha N2, approaches K1, the growth rate of species 1 approaches 0 as well. Thus, the greater the population size of the competing species, the greater the reduction in the growth rate of species 1. The simplest way to examine the possible outcomes of competitions using the Lotka-Volterra equations presented is a graphical approach, which is the zero-growth isocline. The zero-growth isocline represents the combined values of population size for species 1 and species 2, at which the population rate of the respective species is 0. This occurs when the combined population sizes are equal to the carrying capacity of that species. First is the zero-growth isocline for species 1. So when the carrying capacity is greater than the combined population, the population growth is greater than 0, and the population of species 1 can continue to grow. An increase in the population of species 1 is represented by a horizontal arrow pointing to the right. The arrow is horizontal because the x-axis is represented by the population of species 1. However, when the carrying capacity is less than the combined population, the population is less than 0. Thus, the population growth rate is negative, which is represented by the horizontal line pointing to the left, and the population size declines until it reaches the line. The same approach can be given to species 2, but the arrow is vertical because the y-axis represents the population of species 2. When the carrying capacity is greater than the combined population, then the population of species 2 can continue to grow, which is represented by the vertical arrow pointing upward. However, when the carrying capacity is less than the combined population, then the population of species 2 declines until it reaches the line. This is represented by the vertical arrow pointing downward.